Thank you so much. Today's session is a problem session, so I just proposed this problem to solve by using some very elementary manner. I mean, by using some orthogonal polynomial theory. So here, previous my talk, so I already introduced some some discrete Toda lattice. So that is, this one is slightly generalized. I mean that we put some non-autonomous parameter S of T. So S is a kind of a shift parameter. And here we will solve this non-autonomous discrete Toda lattice on a finite lattice. And this is a finite lattice condition. So previous PBS, so in order to connect or relate with box-and-box system and Toda system, we better to introduce some finite system of Toda lattice. So this is such a corresponding condition on this model. And so yes, previous time. Sorry,
Explain a little bit more about this, the shift parameter.
So next slide doesn't appear here. In my okay, sorry. So we will start from the introduction of this non-autonomous discrete Toda lattice. So this, okay, sure.
Toda lattice, you mean is two-dimensional or one-dimensional?
This is one-dimensional case. One plus one-dimensional case. This is the 1 plus 1-dimensional Toda lattice. Yes, and this is already appear in the field of numerical algorithm. So this is intersection between integral system and numerical algorithm will bring us some corresponding ultra discretizable rational mapping. So ultra discretizable means it doesn't contain any subtraction to compute the time evolution. Okay, so this is our model. So previous lecture, we already introduced some discrete differential QD algorithm, which will be is just exactly same as the discrete tolerance in subtraction free form. So here we don't contain any subtraction. But in this case, we have generalized to the shifted version.
So the shift is an arbitrary function that you're using, or what is it?
This is the arbitrary parameter.
Okay.
And maybe it's better to explain in terms of algorithm. So next slide, I show you. And in this case also, we have some corresponding subtraction freeform, but here we are mostly showing how this shifted parameter plays some role. And you see in the previous session, I mean, so this discrete Toda can compute the corresponding eigenvalues of three-diagonal matrix. And but here we have introducing some new parameter delta. This is a shift parameter. And here you see in each step we can choose not arbitrary, but very not completely arbitrary, but at some under some restriction we can freely introduce this delta t. And here, yeah. It means that this will change, this will shift the eigenvalue original A0, so original starting three-diagonal matrix. So this is some asymptotic behavior for Q and E in T to the infinity. So in T to the infinity, E converges to the 0. So L should become to the diagonal matrix, and R will be, so each element give corresponding eigenvalues of original A with shifted one. Okay, so and in numerical system, this R plays a role of acceleration of convergence. If so we know the convergence rate of original QD algorithm. So by introducing this shift operator, the very drastically convergence speed will be accelerated. So in this case, delta t we can choose as we want. Okay. And then so this problem I mean, the discrete, non-autonomous discrete Toda lattice can be solved by using the orthogonal theory of orthogonal polynomials. So that is why I want to introduce some introduction to the orthogonal polynomials as a problem session. Okay. So this is a very elementary one. So starting from very elementary stuff. So we will mostly here we consider the monic polynomial system. So monic means the highest term, the coefficient of highest term chosen as a 1. Of course, we have another normalization like orthonormal polynomial. In this case, highest term, highest coefficient should not be 1, but here we mostly deal with the monic case. And also, we will consider the linear functional L. So L act on the polynomial space to the some constant C. And the corresponding moments, so nth degree of moments can be introduced by using this linear functional. Okay. And also, of course, we can assuming the orthogonal polynomial should have some this type of orthogonality relations. This is a very standard one. And maybe some people is not so familiar with this stuff. So firstly, I will just show you there are several definitions on orthogonal polynomial system. And this is the orthogonality relation for orthogonal polynomial system. If here we are assuming the monicity, but basically orthogonal polynomial system with respect to the linear function L can be defined this one or this one or this one. So all of them are equivalent. And here is the standard orthogonality relation for Pn and Pm. But it's possible to rewritten in this way. So Pn and some monomial x to the j. So if j is less than n, then should be 0. Only j equal n, some non-zero constant hn should be appear. So we may say this hn has an orthogonal constant hn. And then this is a three-term recurrence relation, also possible to define some orthogonal polynomial system. But in this case, some polynomial system satisfy this type of recurrence relation. Of course, this recurrence relation is nothing but a Jacobi matrix, which was Professor Geftman introduced discussion many times. And also, this is a very important point that un should not be 0. This non-zero constant and the non-zero condition is also crucial to introduce the orthogonal polynomial system. And also, so this P and X, n is the nth degree of polynomial with monic polynomial is written in this way. So mu n is previously defined that this is a moment. So some moment should exist. And this delta n is a Hankel determinant of degree n. So these are equivalents. So yeah, it's very elementary way. So how to relate or how to understand these definitions as an equivalent. So first one is definition of PS from 1 to 2. So orthogonality relation shows up gives us a three-term recurrence relation. It's just put in the we know about x times Pn. This is n plus 1 degree polynomial. And it's possible to expand in terms of some polynomial system itself, Pj. Because each system, Pj denotes some jth degree of polynomial. So this is a base of polynomial space in Z, in X. So just plug in this expression to this expression. So x times Pn times Pm. So linear functional will give us corresponding values. Of course, here we are assuming n. So this is an assumption for n and m. So this order we can choose. So of course, this is possible to choose. And n and m, so n is less than or equal to m. And here, you see, so under this condition, sorry, Pj, Pm. So of course, by using this orthogonality relation, sorry. Yes. So J should be, if J is equal to M, then some non-zero constant will be appear as a Hn. So this is some evaluation. And also the other evaluation is possible. And if N is less than, larger than M plus 1, then if, so the X, oops. Sorry. Yeah. So, yes, okay. It's possible to expand the, so we, okay, yes, I will. Like, yes. Okay. We will considering. And we will. Okay, that's good. Yes, so if the X multiply into the latter part, then expand with same manner. And the Pnx is also with less, if under this condition, every term will be less than, so n plus 1 is smaller than n, so it will be 0. So this implies that C and M, if n, so this condition holds, then all coefficients should be 0. This will give us a three-term recurrence relations. It is quite clear. And also, we want to say about non-zero condition upon the coefficient un. So if n is n plus 1, then you see this Pnx is multiplying x to the same power n, which will give us a Hn. So and also equating with above equation, we will have this type of equation. So in this, and that's also Cn n minus 1 is this coefficient of three-term recurrence. And this equation gives us a un, the expression of un can be written in terms of this non-zero ratio of non-zero constant Hn. Yeah. So if Hn non-zero, this un also should be non-zero. This is a non-zero constant will be up here. Okay, sorry for some. Okay, so I tried to show in, so maybe here I want to, just quickly I show you. This is the definition of OPS, and from automatic relation also gives us a determinant expression of also polynomial. It's just solving the condition in terms of mu and dn. So dn is the expansion coefficient of a polynomial system. It's possible to solve in terms of by using the Cramer's rule. This is a determinant expression. And also, so from this expression, we also think possible to construct the delta n should be this equation hold, and which will lead to the this Hankel determinant can be written in terms of a product of orthogonal constant Hn. And of course, reverse formula also is possible to show, but maybe I will skip. And also, this is a point that all stuff can be written in terms of moment. This is very important to analyze or to consider the exact solutions. So we have a three-term recurrence relation. So here, Bn, Un also we want to express in terms of moment. So here is the Hn. So already we know that the Un is can be written with ratio of Hn, and also Hn can be written in this ratio of Hankel determinant. So already we already proved. So plug in, so together Un can be expressed with ratio of this of Hankel determinant delta n. So and then this by using this expression or starting from this expression, this Bn also possible to express So here, slightly different. The last column is shifted by 1 with n, and the Bn is written also moment. Okay, at this moment, this is the point. And also, Fabat theorem shows us the starting from the three-term recurrence relation will give us a corresponding linear functional. So it's a very constructive one. So of course, starting from the three-term recurrence relation, we can uniquely determine the monic sequence of monic polynomials like this. And also, we will use the orthogonality relation with this one. This is not full of, there are many kind of orthogonality relations, but we took the sum of them with this one. And from this one, so for example, P linear function of P1 should be 0. This is also orthogonality relation. And this will give us a expression of mu1 in terms of Bn and Un. So similar situation happened for P2x. So just by computation, mu2 also possible to express in terms of Bn Un. Bn Un is the coefficient of three-term recurrence relation. And the previous talk in Professor Gefman, this moment should be written with power of Jacobi matrix, and one element should give us a corresponding moments. And it's easy to do. And then, yes, also this is only partially we use the orthogonality relation. The rest of the orthogonality relation can be also easy to show by using this repeated use of three-term recurrence like this. So if this is easy to say that also P and x to the x to the n. So x to the, if j is n, then should be non-zero constant should be appear. So non-zero condition will be proven in this expression for this one. So this is the Fabat theorem. It's quite important starting from the Jacobi matrix. And also, we want to consider the finite orthogonal polynomial system. So in order to express this moment, so this is a Gauss quadrature formula, also very famous one. And this is, okay, we have a sequence of orthogonal polynomial with respect to linear function L. And we only consider the finite set of polynomial system. Then, so at some point, Pn is it corresponds to the size of Jacobi matrix. So P and X can be considered a characteristic polynomial of Jacobi polynomial with finite size, and so it means that P and X. So we will consider the zero of nth degree of polynomial Pn, so as lambda j, and this lambda j gives us corresponding eigenvalues of Jacobi matrix. And in this case, so linear functional to the pi x in this case, any polynomial of at most 2n minus 1. In this case, all linear functional, the value of linear function should be given in this summation formula. So W0, W1, blah, 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 these constants should be related to the original Pm. And this is also easy to show. And so let's factorize this characteristic polynomial P capital N like this. And so pi x is the polynomial of degree at most to capital N minus 1. And we can consider some quotient formula. So divided pi x can be, if we can divide with P and x with quotient and some remainder. So in this case, ln x could be less than capital N minus 1. This is all Rn and Ln is some degree of polynomial. And lnx, yeah, also given. So here we are assuming the lnx. So lnx could be given by a Lagrangian interpolation polynomial. So Lagrangian interpolation polynomial is defined by using this condition. Of course, Ln lambda j is at most capital N minus 1 degree of polynomial. So this condition will fix the all term of coefficients with this one. And the expression also known in this way. So in this case, pi lambda j is so this value of pi x, or in x is lambda j. So this is a value of pi lambda j. And of course, this is given. If you know pi x, it's easy to calculate. And also, ljx is given in this way. So you see, this pnx has some big feature with if put the lambda k. So if j and k is same, then should be 1. But if j and k is not equal, is different, the integer, then 0 will happen. So that is easy to solve. And after that, this linear functional could be explicitly written in this way. So you see this. So we want to obtain this type of formula. So L pi x will be, so pi x, this expression we are just plugging into this way. And here we use the authority condition, authority relation for Pn and Rn. So Rn is the degree of Rn. R capital N is equal or less than capital N, sorry. Maybe so less than, yes, sorry. I should delete the equal. So thank you so much. And it should, in this case, could be 0, of course. And then the rest is only this one. So lnx has the x dependence only appear in this part. So linear function only applying to this course. And this could be some polynomial. So it means that this value can be considered as wj. And pi lambda j, this is coincide. So this wj, in fact, is possible to express with this expression. And also, we already know about moment itself. So how to express moment in terms of coefficient of three-term recurrence relation. So in this sense, this value also we already know. So everything was completely understandable, or completely explicitly we can express everything. And then, okay, just summarize the finite orthogonal polynomial system. So we will start from the some three-diagonal matrix. But of course, we can consider the some characteristic polynomial should be appear as the end of three-term recurrence relation should be put in as a slightly not good shape. But if we list assuming x could be eigenvalues of this three-diagonal matrix, and then this Pnx should be 0. So standard eigenvalue problem for three-diagonal matrix will be appear in this case. So completely coincide with our case. Okay? Okay, of course, this is already. And also we have already established some orthogonality relation among a finite number of polynomial systems. So here, n and m should be taken 0 to capital N minus 1. This is already known. And also, if n and m is 0, then, if n and m are equal, then some non-zero constant will appear. But for characteristic polynomial, only we can obtain this orthogonality relation, because we don't say about Pnx to the power Pnx himself, if we don't say nothing about. Okay. And then moments also focus. After that, this is just, sorry, some of people already well know this stuff. But how to understand this orthogonal polynomial system, how to relate with integrable system, especially non-autonomous Toda system. So also this one also well known some transformation for orthogonal polynomial, so-called Christopher transformation. And here, this is only some polynomial system, sequence of polynomial system can be transformed into another sequence of a polynomial system. So this is a Christopher transformation. So you see, so Pn is already, this is our original polynomial system. And the Pn star is a new polynomial system. So by using this, it looks like a rational transformation. So Pn star could be rational function. But this, if Qn taken as this one, so in this case, if we put the x to the lambda, denominator and the numerator has a zero factor. So should be cancelled. So which will give us a corresponding degree of polynomial. So this is also nth degree of Pn star, also nth degree of polynomial, with different with original Pn. Okay.
By L'Hopital's rule, you can get what Pn star.
Oh yes, yes. In some sense, it's quite clear. And but what is the Pn star? The low Pn star. Actually, this Pn star gives us a new orthogonal polynomial system. So this is a transformation among some orthogonal polynomial system transforming into another orthogonal polynomial system. But and also lambda, we can put some how spectral transformation can be changed. So this is some arbitrary parameter. But we have to assume that Pn lambda should not be zero for all n. Otherwise, some zero division will happen. And okay, and maybe I have to take care about how many, which time is my final?
You have until 3:15.
15, okay,
Yeah.
okay, thanks. Maybe it's okay, enough. And here, so we will also introduce some new linear function, L star. L star is defined like this one. So L star is given the original linear function with addition, some factor x minus lambda. This gives us a new L star. And the new moments also same as manner, but we will some explicit expression, some explicit relation between old moment and a new moment like this. And then this is a proof of this Pn star really also in a polynomial system in this case. So, okay, sorry, should be star, sorry, I mistake. But anyway, new polynomial system P star, so Pn star with x to the k will be related in this way. So you see that this is, if k is smaller than n, then it should be 0. And if the k is k equal n case, some qn hn should be appear. And already we have assuming qn should not be 0, and hn is non-zero constant. So hn star also new orthogonal constant should not be 0. Okay.
You have an extra factor of x minus lambda. I think that is not Pn star, because the x minus lambda is cancelling the denominator.
Yes, yes, yes.
But so the left-hand side is not Pn star.
Okay, yeah. This is it's a P star n, sorry.
No, but there is an extra x minus lambda.
Appear here, you mean?
Yes.
Okay, this is the definition of this x lambda. Yes, yes. So that just cancellation should appear, of course.
Just to make sure I understand your hypothesis, lambda is root of none of the p's, right?
Yes.
Okay.
Yes, yes, yes. Sure. And then also we have, we know some inverse transformation with respect to this Christopher transformation. And yeah, I skip. And here, this is the inverse. It means that if we have a Pn star, it's possible to introduce we can return to the original polynomial sequence Pn. So in this case, also a polynomial sequence. And you see the Pn can be expanded in terms of Pn star like this, and plug into this expression. And you see that almost same as same discussion before. So in this case, we can say that this Pn can be expanded only 2 terms. So Pn star and Pn minus 1 star. This is happen. And actually, so starting from these 2 transformation, so we can introduce some discrete time evolution from forward step and backward step. Yes.
Are Pn and Pn star dual in some sense? Is there some kind of duality related?
Duality, bit different meaning, I think. It's just inverse transformation. Yes. And actually, original Geronimus transformation, so inverse transformation, sometimes called as a Geronimus transformation, and it means that the more general idea. But here we use a restricted one. But anyway, this we can show. And we can apply this spectral transformation not only one time. Second time, we can repeat this transformation, which will bring us the time discrete evolution. So here, Pn star, star. So in this case, each time we can choose the spectral parameter lambda prime, lambda blah blah blah. So actually, this is our shift parameter S. Okay. Okay.
Sure. So at each step, you have to look at all the zeros of all the polynomials and make sure that your new lambda is not going to be any zeros.
Actually so. Yes, this. And then, so these 2 transformation, we have Christoph transformation and inverse transformation like this. So we know about Pn is eigenvalue of some eigenvalue, 3-diagonal matrix. And this is a bidiagonal expression for some relation. And PNT also some bidiagonal matrix. And this is just. So we can consider some compatibility condition of these 2 transformations. Both of them are linear equation. So if we have a 2 linear equation, we have to consider the compatibility condition to obtain the nonlinear system. This is a standard technique for integrable system. And actually, by considering this compatibility condition, we will obtain the non-autonomous discrete Toda touch. This is just our case. And so maybe I don't want to write down, so I just put on the slide. So we will consider the compatibility condition like this. And you see, ST and ST plus slightly should be changed. But anyway, final result is not so difficult, that this relation should hold. So BN is just a middle term of 3-term recognition, and the UNT is just bottom of coefficient. So each of them should be written in this way. So here, naturally, we can introduce some non-autonomous parameter ST. So ST or ST plus 1. And here, at this moment, this equation will contain some subtraction to compute the time evolution. But already we know the 2 relations for Christopher transformation and Geronimus transformation. So if we know these 2 linear equations, we can introduce some new positive dependent variable like this. So this is our Christopher transformation and the Geronimus transformation. So slightly shifted. So here we can delete this middle, so Pn plus 1, T plus 1. We can kill this term by using 2 relations. Then we will obtain the other type of relation. It's of course it's not independent one, but it will bring us a new dependent variable D and T. So from this term. And also, I also pointed out that this transformation can be written also in terms of a bidiagonal matrix system. In some sense, this is should be closely related to the, some totally non-integrable matrix. So of course, every totally negative matrix should be decomposed into the bidiagonal matrix. So could be interpreted from this point of view. But anyway, this dn is also, we can check that this dnt has a good feature. It's if under some condition, dnt could be the positive one, even such a expression leads to some minus value we can expect some negative value, but indeed this is positive value. And then by introducing this dnt, the non-autonomous discrete Toda lattice can be written in this way. So this is a subtraction free form. So this is a very desirable expression. Okay, maybe after that okay, maybe we have to. So in order to, okay, so in order to compute this dn plus 1 plus bn plus 1t, and then we are assuming some monicity for st. If st has some decreasing condition, will bring us, it's possible to apply this ultra-discretization limit. Okay. So this discussion also, maybe tomorrow I will show how to do that. And then after that, even after introducing the spectral transformation, every term should be written in this way. So hn, qn, en minus 1, everything was done because so this expression is, okay. So qn plus 1 can be written can be expressed with ratio of pn st plus 1. So if we put x to the s plus 1, this term will disappear, and we can solve pn t plus 1 with divided by this one, and just transpose to the other side. Then expression can be obtained. And already we know about every polynomial can be written, everything was written in terms of moments. And here, polynomial system also has a very good expression. So this is our Pn lambda. So I put the x to the lambda. So this is the expression of nth degree of orthogonal polynomial. And by some very trivial elementary operation for determinant will bring us this expression. And then we can, diminishing the degree of determinant will bring us this expression. So you see, so this one is, so mu1 minus lambda mu0. This is just a new moment from the L star. So just coincide with the time evolution of starting from the cross-check transformation. So in some sense, in this case, Pn lambda can be written in this way. So delta n is Hankel determinant, and the delta n star is just time shifted one. So polynomial system is written in this way. So by using this trick, hn, qn, en minus, everything was written in terms of Hankel determinant. This is quite clear. And the dnt also written in this way. So ratio of delta n and Hankel determinant and some sigma. Sigma is slightly different. So it's also explain why this sigma and sigma will be appear. But anyway, this expression we obtained. And then, okay, the last task is we want to show the convergence property of this system. So here we know about this expression for moment. So this is a Gauss-Quadrature formula will give us this term, and this product is coming from the introduction of Christopher transformation. And then mu and hat is the same. Anyway, this by using this Cauchy-Wiener formula, this tau function, Sorry, tau n is my supervisor Hirota sensei, so I prefer the tau function. But so tau n t is delta n t, and tau n hat is sigma. Sorry, I missed a typo here. Okay.
You call it tau because it's a tau function or something?
Yes. Yeah. I like it. Anyway, we have this type of expression by using the Cauchy-Binet formula. Yeah, and then after getting this expression, it's easy to say that the convergence problem for discrete, non-autonomous, even the non-autonomous discrete Toda lattice. But in this case, of course, here we have to shift parameter at some point, usually in the application meaning, S should be taken as a constant. And ST, if the ST is taken as S, then we just consider this order, and then this Hankel determinant will have this asymptotic behavior, and then finally Q and T will give us this term, and En should be converged to the 0, and we will establish some sorting property for non-autonomous discrete Toda lattice. Okay, and you see by using the orthogonal polynomial theory of orthogonal polynomial, we can rather easily introducing some non-autonomous system of discrete system. Okay, I'm slightly speed up, but it's better to stop around here. But I comment on the continuous limit. So continuous limit also through from the level of exact solution we obtain here. Okay, so I will stop here. So.
People have more questions?
So I missed some variables because you show so many variables. Mm-hmm. So Q and E, Q and T and E and T, they are written as a ratio of delta over delta like that, and a D. The D in the so D is a little bit different because it includes sigma there.
Yes.
And what does it mean?
Yes. First, I'd like to show this D and T is given in this way. So this is our equation which introduces this dependent variable Dn. So you see, if we put x to the s plus 1, this term will be disappeared. And then this term should be written in this form.
Yes.
After that, by using this formula, so slightly different. Lambda is lambda t or st, s of t.
Yes.
But previous one, d and t, it should be if you have to put the st plus 1. It's a shifted one.
Yes.
So this sigma means choice of spectral parameter. The order is slightly different. And also, yeah.
Yes. Mm-hmm.
Yes, if we write down in terms of bilinear form, Hirota's form, this sigma is very weird term. It looks like a non-symmetric term will appear, even if the bilinear form should be symmetric form.
Yes, so delta satisfies bilinear equation.
Yes, this one also.
Sigma is also only by sigma.
No.
So
okay.
you mix sigma and delta.
Yeah, I just show you actually, I'm already preparing this. Okay. Plug in this expression to this origin our nonlinear, non-autonomous discrete Toda equation. So D has some weird sigma tau function will appear. And then plug into the first equation, we obtain this equation.
I see.
So
Yes.
this tau is a Hankel determinant, and sigma is also, in some sense, same as a Hankel determinant,
Yes.
but some
is
parameter
shifted.
is different. And also, in case of an autonomous case, the only one kind of tau function will appear, and the single linear form is enough to describe the autonomous discrete Toda. But in case of a non-autonomous case, we have to introduce some coupled system of tau function, like this. So of course, it's not so bad, but this form is quite weird. But I can explain why this situation happened from the point of view of Hirota-Miwa equation or discrete KP. And this is meaning of sigma. So usually we will considering the straight time evolution. So tau 0, tau 1, tau 2, this is time evolution. And in each step, we can introduce a new parameter, alpha 0 and alpha 1. But we can exchange the order of parameter by introducing sigma n1. So sigma n is spectral transformation with different parameter, alpha 1. And then alpha 1, so another spectral transformation for sigma introducing alpha 0, which go back to this single time evolution. It
Because
works?
these two evolution is commutative?
Yes, of course, of course.
I see.
It's a hierarchy of, taken from the
yes.
hierarchy of Hirota-Miwa equation.
I see. So,
And then, so also it's still strange because of some symmetry will not appear. So this is my understanding for this one. So we have to introduce another time evolution. So K1, K2, so K1, one of them is just T, and the other was some auxiliary independent variable. So here, if we introduce some stair type time evolution in this 2+1 dimensional space, so some reduction. And of course, we can think about this stair type time evolution step as a discrete time evolution. It's possible, of course. This is our choice of. And then, so you see, so this is some t. It's taken from -1, 0, 1, 2, 3, 4, 5, 6, 7. In this way, we will choose the standard time evolution t. And then sigma is taken from, so just this time linear form is a relation among these square.
yes.
And here is square, here is square, here is square. In order to put the additional term as a sigma, and then sigma n, sigma 1, sigma 2, sigma 3, 3, 4. So we can introduce the corresponding tau function on this one.
I see. So originally the variables q and e are a kind of positive variables as a coordinate. But how about d?
D also
positive.
positive. Yes.
So what is how to say? Q and e are some pair.
Yes.
But is there any partner of d?
In some sense, we have to introduce one more set of Toda equation. So we can couple. Yeah. It's possible to couple. Not so. Of course, it's independently we can introduce Toda system, but we can non-trivial mixture can be done. also possible to use the theory of orthogonal polynomial. So this is my today and tomorrow's my topics actually.
I see. Thank you.
Yes, you're welcome. And I also stress that discrete autonomous system and non-autonomous system is quite different. Even if we only introducing such shift parameter, but the structure of integrability, I mean that the binary form structure is a big difference. So one of them is just single equation, but the other one, I mean the non-autonomous system, we have to introduce the coupled system. This is quite different. So also, this is some difficulty to generalize, or de-autonomization is sometimes very difficult. So, but tomorrow I would like to introduce, it's not so difficult if we considering the theory of orthogonal polynomials, like non-autonomous Toda system. You see that the non-autonomous Toda system is quite natural, no difficulty at all. But we can obtain such non-autonomous system. Is it okay?
Questions? Okay, so thank you. And